What if Tabby Star was real? What would we even see? A postdoc at Yale named Tabetha Boyajian was looking for something else. The Kepler Space Telescope had been staring at about 150,000 stars for 4 years, watching for the tiny brightness drops that mean a planet has passed between the star and us. The data was a fire hose. NASA needed human eyes to sift through it for the strange cases. Boyajian volunteered for the citizen science platform Planet Hunters, and she was about to find a star that no planet could explain. In 2011, Kepler recorded a brightness drop on a star, catalogued as KIC 8462852. Not 1%, not 5%, 22%. The star dropped to a fifth of its normal brightness for about a week. Then it recovered. In 2013, the same star dropped again, this time in a different pattern, a long, slow fade that lasted several days. No known natural object orbiting a star could dim it by that much without being seen directly. The data had been sitting in the archive for years. Boyajian pulled it in 2015, ran every standard test, and published a paper with the calmest possible title in astronomy, Planet Hunters 9, KIC 8462852. A planet transit makes a clean, repeating curve. The star dims by a small percentage, then brightens again on a predictable schedule. Tabby Star does the opposite. The drops are deep. They last days or weeks. They are not periodic. The 2011 event dimmed the star by 22%. For comparison, a Jupiter-sized planet transit dims a star by about 1%. Even a giant planet would not drop 22%. You would need an object roughly half the size of the star itself. Then there is the shape. Kepler recorded brightness every 30 minutes. A planet transit gives a smooth, symmetric dip. Tabby's star dips are jagged. Some show sudden drops. Some show stair-step patterns. Some drop in a way that suggests the occluding object is not a clean sphere, but a loose, broken-up structure with denser and thinner regions. The asymmetry is the key. If a dust cloud were orbiting the star, you would expect it to appear in front of the star at regular intervals as it swings around. KIC 8462852 has done its biggest dimming events only twice in the 4 years Kepler watched. The interval was 750 days. The drop depths were 22% and 8% in completely different patterns. No natural object explains the irregularity and the magnitude together. Boyajian's paper tested 7 natural explanations. Each one failed. A normal dust disk was ruled out by infrared observations. The star does not have an unusually bright infrared signature, which any thick dust ring would produce. A planet being torn apart by the star was tested. The timescales and dimming patterns did not match. An asteroid belt in the early stages of collision was considered. The amount of material required to dim 22% is larger than the entire asteroid belt of our solar system. A cloud of comets was the front runner. A swarm of broken-up comets passing in front of the star. But the comet hypothesis requires the swarm to be in a very specific orbit that the data does not support. The 2013 event lasted days longer than any comet transit would, and no comet swarm has ever been seen to dim a star by 22%. A failed planet called a brown dwarf was suggested. That would also produce a long, slow infrared signature that has not been found. The star's variability between dimming events is also not what you'd expect from a binary companion. After every natural test fell through, Boyajian's team published a second paper in 2016 that simply listed the impossibilities. The data refused to match anything the universe is supposed to do. Avi Loeb is a theoretical astrophysicist at Harvard. He chairs the department. He is not a UFO enthusiast. In 2016, he co-authored a paper that put the alien hypothesis on the table, not as a guess, but as a logic step. The argument is simple. The dimming pattern is consistent with a partial Dyson swarm. A Dyson swarm is a collection of solar panels built around a star to capture its energy. If a civilization wanted to build such a structure, they would not build a complete sphere. They would build a loose, irregular swarm, exactly the kind of broken, asymmetric pattern we see in the KIC 846-2852 data. The dimming is too deep for a single object. A swarm of many smaller objects would explain the jagged, stair-step shape. Loeb was clear about what the paper did and did not claim. It did not say aliens built it. It said the alien hypothesis has not been ruled out and that we should look. SETI pointed the Allen telescope array at the star. The Breakthrough Listen initiative did a radio survey. No signal was found. That does not rule out a swarm. A solar collector would not be transmitting. It would just be in the way. A 2018 paper by Caltech astronomer Natalie Mashian proposed a different answer. Maybe it is comets. The hypothesis. About 10,000 years ago, a large star passed close to KIC 8462852. The gravitational pull ripped apart a large comet. The debris settled into a tight orbit. Over the following centuries, the fragments continued to break up. The largest fragments passed in front of the star in 2011 and 2013, dropping the brightness by 22% and 8%. Smaller fragments continue to drift in front of the star, creating the smaller dips. The problem with the comet hypothesis is the mass required. A 22% drop in 2011 means a swarm, roughly 10 times the mass of Earth's moon, must have passed in front of the star. Such a large comet swarm is not impossible, but it would also have produced a bright infrared signature that has not been seen. The 2018 paper addressed this by suggesting that comets are very cold, colder than typical solar system comets. Whether such cold ancient comets can exist is itself a question. The Mashian hypothesis is the leading natural explanation. It is also incomplete. It does not explain everything, and it predicts things that subsequent observations have not confirmed. But it is the best model we have so far. In 2016, Bradley Schaefer at Louisiana State University dropped a bomb. He pulled photographic plate archives going back over a century and reported that KIC 8462852 had dimmed by about 14% in total between 1890 and 1989. The star had been slowly fading for 100 years before the Kepler data even existed. If Schaefer was right, the comet hypothesis was dead. A single comet swarm could not have produced a 100-year dimming trend. Whatever was blocking the star had been getting in the way for a century. Then came the rebuttal.